Engineering 305. This is chapter 7. We're working on sections 1 through 4, which is an introduction to beams. There you go. The course learning objectives. The course learning objective for this section is we're going to, at the end of this, and that's not entirely true. It says calculate the normal and shear stresses in beams. Those are the long-term goals for the beams section, chapter 7 and 8. For this lecture, it's only calculating normal stresses, only the normal stress in the x direction, and we'll talk about that as we go. The equations from the study guide are these two, that the normal stress in the x direction is equal to negative m sub r, which is, I guess we'll talk about that, m sub r times y divided by I. Now, m sub r is the moment at that's the reaction moment at that section of the beam. Y is the distance from the neutral axis, and I is the section modulus. All of that we will cover. We do get then this other equation that sigma max, that the maximum normal stress is equal to mc over I, where c is that distance to the extreme fiber, similar to what we had in torsion. I is now the section modulus, which is second moment of area, section modulus. Different, similar, and we will cover that, but those are the things that we need to know about for this section. Those are our two equations that we'll get to actually in section 4 of this chapter. So the first thing that we need to know about really when we're doing beams, and the first thing that they introduce us to in the chapter, is some of the nomenclature that surrounds beams, because if we don't understand the language, it will be hard to talk about. So the first thing we should talk about are the different types of beams, and this is the figure from the very beginning, the opening section of the book on the different types. This first beam in A is a simply supported beam. By simply supported, what they're meaning is that there is a support on both ends that is transmitting a vertical force. It's a force in the y direction, but it's not providing a moment. So it's a simple support. It does a force, but no moment. And then we get the next situation in B, where the situation in B is I've got a simply supported beam with this overhang. So if I would have, I'm going to use yellow because I think it'll be a little more clear. I'm struggling with my pen here. I'm struggling with my whole display. If I would cut it off there, it would just be a simply supported beam. But because I've got that overhang, it's a simply supported with an overhang. Now, this beam, C, sorry, I got to get my colors right. C, that is not a simply supported. I have 3 supports. Well, if you start thinking about the equations of force and of moments to solve that, there are no forces in the y direction, so I don't get to use that equation. So I only have 2 equations. Sorry, there's no forces in the x equation, x direction. There's only forces in the vertical. I'm going to put a coordinate system on here. So there's my y. There's my x. I only get equations of force in the y. I can sum the moments in the y, sum the forces in the y direction. I can sum the moments, but I don't get to use the x direction equation. There are no forces in x. And so what that means, that results in, is this problem is statically indeterminate. And we'll have different ways of solving that in chapter 8. The other big boundary condition that we're going to look at is this here, pen issues. And that is a boundary here, which is some more, it's supporting, not only is there a force, but there's a moment, and that's called a cantilever beam. That is a cantilever system, and it has a force and a moment. Now, again, I have 2 equations, Some of the forces are equal to 0, some of the moments are equal to 0, and that joint, that end, that left end on that beam is doing both things. It's giving me a force and a moment, so I can completely define my situation. That is a static situation. I can then start doing other things. Now, I make it much more complicated. I make it much more complicated when I put this support out at the end out here. Pen. I can't get it. There we go. When I put that force out there, that means now, again, it's a statically indeterminate problem. I've got two forces, two vertical forces, one here, and a moment. And that means I've got 3 forces. I can't solve for all that. I have to take into account the strains. Those are actually, I think, I like the statically indeterminate problems and for beams. They are, they're a lot more fun than the other ones. And then the last situation is a fixed beam that I've got a situation. Let me get rid of me. I've got a situation where I've got a force and a moment and a moment. And now I have 4 forces to solve, and that creates its own challenges. It's a different statically indeterminate problem. But we'll approach that, and we'll have new tools available for that. So I want you to recognize, however, that while we're talking about these beams and we're using descriptive words for them, the descriptions are really a mathematical description of the boundary conditions. That word simple, imple, can't touch the screen. That word simple correlates to there's just a force in the y. And fixed means there's a force in the y and a moment. And so those words are used just to describe the mathematics of the boundary conditions. Because for those of you who took the partial differential equations or are taking the partial differential equations class this fall, that may start to make sense as we get into some of the equations that we're going to use to solve these things. And you also have to remember these are all of these deflections are a result of moments. My fundamental diagram for this problem is something where I've got that stress cube and stress cube and a moment acting on either end, causing it to flex, which is what we're talking about, flexure of beams. All right, that's our nomenclature. Now we're moving on to section 2, where we're going to talk about flexural strains. Now, I'd like to show you this, and I'll bring stuff to class and I'll demonstrate this. But when we flex, if I give you a diagram and I draw it like this, or I could draw it, right? I could draw it like that. I don't know which one I typically draw, but I want to give you a situation where I get a smile. I want a smile. So now I'm going to draw this box, and I made it a lot longer. But I'm flexing this system so that it bends down in the middle and I get a smile. And the reason is that's going to be a positive. Of course, we're going to define that as positive. It's happy. It's positive. But now you can see that this top, and you can even see it on this poorly drawn diagram, the top got shorter. The top is shorter. And the bottom got longer. And that's what happens. And there's a stretch depending on, that stretch is there depending on how far I am away from, oh, I've got a term here. This middle, the center of the beam, there's some place in the beam called the neutral axis, and that's where it stays the original length. That's how we define the neutral axis, is that it stays the original length. Now, let's move forward with a little bit of we'll start throwing some math at this, all right? In order to get the math, you got to have at least a diagram or so, and then we'll actually get to the math. Next slide. This is the same diagram kind of that I was drawing. You're seeing a distance to the neutral axis, this delta x. They're calling this that neutral axis. And then there's a distance away from that, which is y. And that helps us define really how much our length has changed. And then we can start talking about strains. And I think you're going to see this is kind of similar to what we did with torsion and twist. But we're looking at, this is following some radius of curvature. Rho is equal to a radius of curvature. Oh, RAID, R-A-I-D. Oh my goodness. R-A-D-I-U-S of curvature. And so then the length of that curve is going to be rho times some angle, and that's this delta angle. And then I can compare the lengths at each of these different heights, because that's rho times that d theta, but the theta is the same for all of them. So now let's look at the following equation. So with those definitions, we get this equation. The strain is equal to, and then you see that equation, they give you delta x prime. What that really is this is just our original equation that we were using all the way back, chapter 3. You can't see me because I had to turn off my camera because I'm going to use the stuff in the corner. But this is my length final minus length original. Let's look at that a sec. Delta x1, that's x prime. That's how much it deflects at that, or how much it changed at that axis, on that axis. And then I divide that by length original. So if I want to see, and I'm just going to start drawing because you can't see where I'm pointing and you can't see me, that p minus y is not p, it's rho. That's this distance y, rho, which is the distance to my neutral axis, minus that distance back up. Y is measured positive in that direction. So then I get an actual radius out to that point of rho minus y. And then the length of that segment, multiply it by the angle. Can't see me gesture again. That was kind of silly. That's my length final. And then minus length initial divided by length initial, or length original. I should be consistent on that. Length original. And that, when I do all the simplification, then I get this over on the end. That's a minus 1 over rho times y is equal to my strain in the x direction. And if the reason, so let's start thinking about that a little bit. I've got a negative sign in there. That negative sign is because as I go up in x, I'm compressing. So if y is positive, I'm compressing and my strain is negative to keep that all consistent. Again, that's part of using length final minus length initial, or length original. The same as using temperature final minus temperature initial. That helps those things develop. My strain on the bottom, that's at a negative y. And so a negative y with that negative is going to make that positive because that's under tension and it grows. So I've got an equation now for the strain in my system. It is based on, if you want to know, it's got a linear distribution of strain. And if you read the textbook very carefully, distribution, you will see that's an assumption that they've got a little wiggle room around. And in fact, if you do a really exhaustive analysis, they'll show you that it's not right. But don't get hung up on that. It's a good equation. We're going to take that forward to calculate our flexural stresses. See if I can get my picture back on. I don't know if that, I don't think that got my picture back on. That's okay. We're going to take that forward to calculate our flexural stresses. And we do that going right back to our equation of our definition of Young's modulus. We've rearranged it. So now, because we're trying to solve for stresses, we know the material property, and we know we've got an equation for strain, so we can make the next step. And that is the stresses are equal to Young's modulus times the strain, which is equal to, it was a minus 1 over rho. Now we're going to put the Young's modulus on the top. So now I've got an equation for my stress as a function of y on that beam. But one more. I can look at the moments across any face, the sum of the moment that's acting on that face, by integrating the moments, such as y df. That's the torque. I'm integrating the torque there. Well, that df is equal to stress times dA. And I have the stress in the x direction as a function of y. So this is all making sense. And then I get the moments, the resulting moments at that cross section equal to, and I start factoring it all out, and I get that. And out of that, you might see some stuff that looks similar to torsion. And what we're getting is that I've got this term here, y squared dA, and I pulled my constants out front. I've got this integral of y squared dA, and I'm going to define that as that's the equation I wrote there. And that is very similar. Sorry, I did not write that very well at all. Y squared dA. That's very similar to J, which resulted because I had the integral of r squared dA. And so that's kind of cool. That's kind of cool. Well, that gets us, all of that gets us to, if I substitute this all in, I've got moments, stress, C, substitute, I'm going to get the flexural stress that I'm looking for. The elastic flexure formula is the stress in the x direction is equal to negative the moment times y, the distance away, over I. And if we think about it, if we go right back to what we had, I'm gonna add this. The stress in the x direction max is equal to, and now I can put I can put the negative or not, but it's going to be mc over I, and that's the equation that I have on the study guide. There might be a minus that you need to take into account, but C is now that distance out to the extreme fiber again. And so you want to remember that. Now, it may be that your maximum stress is positive, as this would indicate when I drop the negative sign, or it could be that it's negative. We often deal with symmetric beams, and so then we've got a positive stress and a negative stress at the same time. And you were just going to have to be paying attention to that. We do get very casual and work with that formula at times, ignoring the negative. But the reason is because we're often thinking about symmetric beams. The next thing we're going to do is we're going to start taking that that stress equation and we're going to start running with it. So our next presentation is example problem 7.2, where we're just going to start implementing this, and we'll start calculating the resisting moment and, excuse me, excuse me. We'll start doing calculations, and maybe we'll do an extra example problem. But the biggest, our equation is now the stress is equal to MC over I. So you've only got a couple things to calculate. We can give ourselves a material property that we can't violate and ask about the maximum moment that we can allow. But realistically, I'm going to guess that C and I they're products of geometry. They're almost always going to be provided for us. And so we're going to be calculating this relationship between the stress and the moment. So, and you can see already in this example problem, we've been given a stress, 15 megapascals. So find the moment. Well, that means we've got to calculate C and I. So, all right. Don't worry, there's more to come.